Okay, let me finish off what we did in class today, and I'll do a solution in Matlab just to show you how this goes, since the homework is very similar to this. So you remember in class we were talking about this statically indeterminate problem, fixed on both ends, two elements, and there's a 1,000-pound force in the middle. We figured out the element stiffnesses, the AE on L's, and this is our assembled global stiffness matrix. Okay. We know that U1 equals U3 equals 0. Those are the essential boundary conditions. And these are the external applied forces. The reaction forces at F1 and F3, those are unknown. Although we solved that in class, okay? All right. So in class, we juggle these equations using equation 2 and the fact that U1 and U3 are 0 to directly solve for U2, okay? Now, what I want to do now is show a more general approach, how you can approximately solve this without doing the equation juggling, because that can be sometimes awkward to do for larger problems, or if you want to implement this in a computer program in general. Okay, so here's our stiffness matrix. Here's our nodal unknowns. And then here is our external force vector, all right? All right. Now, remember, and you can look at this. I'll show it in Matlab later on. But as it stands now, this stiffness matrix is singular. They always will be singular until you apply the essential boundary conditions. Because again, this problem without essential boundary conditions, the solution is not known uniquely for the displacements. You can find the translations, the stretches of the elements, but not the displacements uniquely, because it could actually rigidly translate, okay? It's only once you fix a certain number of nodes. Actually, in this case, you just need one fix, but this problem has two fixed. It's only when you apply the essential boundary conditions that the problem becomes properly defined. Okay. And you can check the determinant on this, and you can see it's singular as well. All right. So how do we go about doing this without having to juggle equations? Well, in this case, we have two essential boundary conditions, one at node 1 and also at node 3. So at each essential boundary condition, we have this unknown reaction force. And we also know, actually, the displacements in the nodal vector, okay? One way to approximate that, okay, and this is what I mentioned in class, the singular system means that you have a linear dependency. One equation can be written as a linear combination of the other equations, okay? And in this case, let's see. You can see right off the bat, if I take the negative of this equation and the negative of this equation, if you take the third row and this first row, add them together and times it by -1, you get the second row. So right there you can see the linear dependency. So basically 3 plus 1 equals negative equation 2. So that's the linear dependency that you can see in this system. And so it's singular. So in a sense, we have not enough equations, not enough linearly independent equations to solve for the three unknowns. We need 3 linearly independent equations. So basically what we're going to do is throw out the sum of forces at the nodes on node 1 and 3. We're going to not use those equations. And we're going to replace those. What I'd like to replace this with is the equation that U1 is equal to 0, and this equation with U3 equal to 0. The actual essential boundary condition equation, okay? Now, there are a lot of ways to do that. You can actually put 1 on the diagonal and 0 on the rows. But a general way is using this sort of penalty approach. It's actually not a bad way to do it. And this involves, for each equation, so let's say you have the essential boundary condition u at node n equals some known value. What you do is you replace, k and n in the global stiffness matrix with a big number. I'll call it B. All right? And then on the force side, you replace force n with an also a very big number times the desired value for the essential boundary condition. Okay? You do this for every node, every n that you have an essential boundary condition. Okay, so for example, if we do that for the first equation, and let's pick our big number. Usually the way to look at it is you want something at least 2 orders of magnitude bigger than the things on the diagonal. So let's pick B to be 10,000, okay? 10,000 megapound inches, okay? I'm sorry, what am I talking about? Let's do 100. We'll do 1,000. 1,000's good. If it gets too big, there's actually some numerical conditioning issues with solving the matrices, but 2 orders of magnitude is not too bad. And actually, you can look at 3 order of magnitude, 4 order of magnitude, and see how it goes. Okay. All right. So if we look now at the first equation, if we do that, what I have now is, just to write the first line, okay, I have 1,000 minus 12 times 0 u1 equals, and now on this side, we put the big number, which is 1,000 times the displacement, the value of the displacement at the node that we have the essential boundary condition. So in this case, it's actually 0. Now if you look at this equation, what you have here is, this is now 1,000 times u1 minus 12 times u2 equals 0. All right? And so what you can see here is the displacements are about on the same order of magnitude for most problems. So this is basically 0 in that equation. It's very small. Okay? And now you can see you're just left with u1 basically is nominally equal to 0. Another way you can look at it is you can say that u1 is going to come out to be 12u2 over 1,000. Okay? But you can see this is going to be this means u1 is going to be 2 orders of magnitude smaller than u2. It's basically going to be close to 0. Okay? All right. Now the second equation we don't have to touch because there's no essential boundary condition there. And now the third equation, again, we have an essential boundary condition, so we'll keep 0, minus 3, and let's put 1,000 here. Actually, we can make it 10,000. Let's go with 10,000. I think for this system it'll be okay. And then, like I said, this is going to go to 0, and again, this is going to go to 0. Now, sometimes you'll have a non-homogeneous essential boundary condition where the prescribed value isn't go to 0, and then this would not be 0, but it would be the same big number times the value you want to set it to. So you can see that that'll go through. Excuse me. Okay, so now this system is no longer singular. I can actually solve this. I can find explicitly K inverse, okay? So you can use that and then you can solve, multiply this by K inverse and you can get the displacements. Well, let's see how that goes. You can do it by hand in a 3x3, but once you get much bigger than that, really, it's kind of cumbersome. So let's look at Matlab. So in this class, when I basically say you can solve it by hand, I mean it's quite acceptable to use things like Mathematica and Matlab. So here's a little Matlab M file. You can use it either as a scratch pad or you can save it. I'll save it as, save it to the desktop. My computer's acting very slow today. All right. And I can just execute it to where we have it. Change directories. Okay. Now, if you look at what's going on here, I took a couple simplifications. First, I clear, because I might rerun this several times, and you want to get everything out of memory. So clear kind of always flushes everything out of memory. I've seen a lot of times where people have some residual things floating around in memory, and they affect their results, actually, in an unintentional way. Then I have the system parameters, the cross-sectional area of the two elements, Young's modulus, the lengths of the two elements, and then the load. This allows me to easily calculate the stiffness of the elements and then define, oops, here, the global stiffness matrix. This is the singular global stiffness matrix. So right here we have the global stiffness matrix and the value of the force. And you can see if we get the determinant of K, it's 0. So if I tried to get the inverse of K, it gives me a singular value, right? That matrix is singular, as we've discussed. Now, I'm going to modify that. Let's just redefine it. Okay, let's put our big number in here. B, 10,000. Well, I have to do 10,000. Let's do, we know it, let's make it a 10,000 times K1 plus K2. So that's just a big number that's always going to be 10,000 times bigger than basically what's on the diagonal, right? Okay. And usually the diagonal terms are the dominant ones. They're the biggest values in this matrix, in stiffness matrices. All right, so now I can modify this. Let's just directly write the stiffness matrix, the modified stiffness matrix. So on this diagonal, I'm going to add B. And then on this point, I'm also going to add B. All right, so that's the diagonal for the third equation and the diagonal for the first equation. And now we're going to modify F so that the first and third values are zeros, but I already put that in there, so those are fine. So here you can see this. This is now my modified stiffness matrix. Oh, B is undefined. I forgot to execute that one. Let's actually call this K mod because it's modified, okay? We can just execute that. All right? And so there you go. There's the modified K. There's the value of B. And now you can see I can actually get the inverse of K mod. It exists. Okay? It's got something here, right? All right. So I can actually solve for the displacement. The displacement is going to be K divided by F. This is the way we solve the system of equations. KD equals F in Matlab. This is better than explicitly finding the inverse. And it got that it's singular. Oh, because I used K, not K mod. Excuse me. I was going to say. There you go. Now there's our answer. All right? And you can see this is basically what we got in class. 0 for the first and third nodes and 0.2 for the second node. That's the displacement. Actually, if you look at it, there is a non-zero value for the first node. It's not exactly 0, and that's the error because we only approximated and forces that essential boundary condition, is that right? So I probably should put this in here. Let's do this, right? So this is actually the solution, okay? So at this point, we're finding the solution, okay? So if I execute that, you can see this now gives us the solution that U1 is equal to, well, let's write them all out. U1 is minus 1.6 times 10 to the minus 8th. U2 is the basically 2.0 times 10 to the minus 4th. And then U3 is now 3.9, or really 4.0 times 10 to the minus ninth. And so these are basically 0, okay? And if I had made that big number bigger, you'd actually see that those would become closer to 0. I could probably put another 2 orders of magnitude on here, and now if I execute it, you can see actually that D1 is a lot closer to 0. It's to the minus 10th, all right? So it's how close that gets to 0 depends upon the penalty term you put it in, the value of B. All right, so now we have the displacements. When I have the displacements, okay, I can now compute the element strains, okay? I can get the element strains. That I can get by the change in length over the original length. And then I can get the stresses just by multiplying E times the strain, okay? And I'm so sorry, you can't see any of that stuff. I'm writing on the page, and I've got Matlab blocking it. I can see it, okay? All right, so you can get the strains by change in length over length, and then multiply it by Young's modulus, and you get the stress. So actually, the strain in the first element is going to be U2 minus U1 over the length of that first element. And the strain in the second element is going to be U3 minus U2, because that's the stretch of that element over the length of the second element. And I can compute those, and then I can get the stress in the first element is the strain in the first element times Young's modulus. And likewise, the stress in the second element is the strain in the second element times Young's modulus. And we can do that easily enough in our little script. So I'm going to call this epsilon 1 for the strain in the first element, and that's going to be D2 minus D1 over the length of the first element, L1, and then epsilon 2, the strain in the second element, is going to be D3 minus D2 over the length of the second element. And then we can get the stress. Stress in 1 is just going to be E times epsilon 1. And likewise, the stress in the second one is going to be E times epsilon 2, the strain in the second element. And so here we can rerun that. And there you go. These are the strains in the elements, and these are the stresses in the elements, okay? So the first element has a 200 psi stress, and the second element has a compressional stress of 200 psi. All right. So this is equal to 200 psi, and this is equal to minus 200 psi. All right. All right, now the last thing you might want to do is get the reaction forces, okay? And when we did this, actually you can see when we made this approximation, we lost the actual values of the reaction force here. But we know the displacements. And if you look at the original system, you can see the reaction forces are what you would get if you took the original unmodified stiffness matrix, the singular stiffness matrix, and multiplied it by the known displacements. Now we know all these displacements, so actually we can recover the external forces. So to get the reaction forces, you can take the original stiffness matrix, not the modified one. This is the one that's singular. Multiply it by the solution, and this will give you the reaction forces, all the forces. But you can look at the net force at nodes 1 and 3, and that'll give you the actual reaction forces. So we can do something like that in here as well. We can modify this, and we can get F reaction is equal to K, that's the original stiffness matrix, times the solution, D. And now if we run that, here are the reaction forces, and you can see at node 3, it's the applied 1,000 pounds. At node 1, it's the 800 pounds to the right, and at node 3, it's 200 pounds to the left. So they give you a net force of 0. Where does that seem odd? Oh, that's... Wait. So here we go. So 1,000 pounds acting in that direction. This is 800 pounds, and that's 200 pounds. And something's a bit odd here because I'm not sure what's going on. Why did that not come out correct? This is P. I want to put P here. They should balance out. Ah, I'm sorry. I put the stiffness matrix in wrong. That's why. That should be K1 minus K1. That's the answer. It's going to change a couple of things. Actually, the displacements are still nominally the same. But okay, that was the problem. I had written the original stiffness matrix incorrect right here. Okay, I had a -1 here. All right, sorry about that. But now you can see, okay, now that makes sense. This is actually 800 going that way, 200 going that way, and 1,000. Now we're in balance. The displacements will turn out to be the same. The stresses worked out to be the same because of the, basically the displacement is still 0.2 and 0 and 0. Okay? So that's how you go about doing this stuff. So this is Matlab is a nice way to kind of help simplify the problem. All right? Sorry about that mistake, but I have to stop now and go to a meeting. Okay? Bye-bye.